We're now going to go through a couple of examples to uh, illustrate the process by hand calculations and also how you would do this in StatCrunch. The first example we're going to do is a dependent samples or paired samples. And the example we're going to look at, again, remember that in order to do paired, they're matched together. You either have something that's before and after, or with and without, or specifically says these are paired together. We calculate the test statistic by creating a new variable called the difference. Because they're paired, we can make this difference variable and it makes sense. We'll call that difference mu sub d. We will test the null hypothesis that the difference is equal to 0 versus some alternative. The test statistic will be d bar over s sub d over the square root of n. And well, we can have one of three cases, just like we did before. Either the difference is going to be greater than 0 or less than 0 or not equal to 0. So the specific example we're going to look at is a teacher randomly selects 10 students to participate in a week of training designed to improve their typing speed. The teacher times their speed before and after the course. So each student is going to have two measurements, a before and an after. That's indicative of a dependent set of data. We have two samples that we're working with. One is a before score and one is an after score. They are tied together, so this is a dependent test of two samples. We want to know then if the teaching time before or after the course is sufficient to warrant the time and expense of the course. Well, to make it worth the time, we would need to see a decrease in the an increase in the typing speed. So our alternative, or our null hypothesis, is that there's no difference between the two typing speeds before and after the course. The alternative is that after the typing course, our speed has increased so that the after speed is greater than the before speed, or if I look at the difference after minus before, that average difference should be greater than 0. So because these are tied together, I'm going to take my after and my before and create a new variable called the difference. That gives me this column here. I can calculate the average difference by adding up that column and dividing by 4.5. I can also calculate the standard deviation. You could do this in your calculator as well. On your homework, I would encourage you to use StatCrunch to calculate the difference if need be, or to do the test altogether. For exam type problems, I will give you this information. I may tell you the before and after, but I'll tell you what the average difference is and the average standard deviation of the difference, or the standard deviation of the differences as well. So you'll be able to take these and plug them into the test statistic. In this case, we had 10 observations. The average difference was 4.5. The standard deviation of the difference was 5.48. So we plug that in and we get a test statistic of 2.597. I had a 5% level of significance. I had 10 observations, so that means I have 9 degrees of freedom. Remember, it's n minus 1. So to come up with a critical value, I would go to my table. I would look in the 9 row. And the 0.05 column, because this was a one-sided test, and I see a critical value of 1.833. So I know if I exceed 1.833, I'm going to reject the null hypothesis. So our test statistic was 2.597. That does exceed our critical value of 1.833, so we would reject the null hypothesis. If we wanted to know the p-value, we could go back to our t-table. We can look in the 9 degrees of freedom row, and I'm going to look for 2.597. I notice that would lie between 2.262 and 2.821. Therefore, I know the p-value is somewhere between 0.01 and 0.025. If I were doing this in StatCrunch, I could put my data in the 2 columns. So this is the before, or excuse me, this is after, and this is before. And you can see there's a difference column here. Okay. To do this, I will do stat, t-stats, paired, because they are paired together. I want to look at after versus before, and I want the after to be greater than the before, so I want the difference to be positive. If I click this little box, it will show me the differences. And I get then that a t-test of 2.596, roughly. Notice that ours is a little bit off of this because we did round in our process of calculating the standard deviation, but we're close. We see an exact p-value of 0.0145, which is between the 0.01 and 0.025 range that we saw in our table. So that's the process you can go through for calculating it in StatCrunch. And if we go back to it, you can see that this is the information I get. Mu1 minus mu2 was the difference between variable 7 and variable 8, which I had called after and before. So the second example I want to do is one where I have independent data. And for independent data, remember that we're going to use this Welch's t-statistic. For this particular problem, we're looking at British health officials have recently expressed concern about problems associated with vitamin D deficiency among certain immigrants. Doctors have conjectured that such a deficiency could be related to the amount of fiber in a person's diet. The chemical compound H labeled 25-hydroxyvitamin D3 is the major circulating form of vitamin D, and its plasma half-life is intimately related to the body's vitamin D level. An experiment to compare the levels in 2 groups is taken. One group is placed on a normal diet. The other is placed on a high-fiber diet. Note that I no longer have a relationship between subjects. I don't have somebody where they followed a normal diet for a while and then a high-fiber diet so that I had 2 measurements from the same individual. I have 2 completely separate groups of individuals. One is on a normal diet, one is on a high-fiber diet. There's no way of matching those up, so these are independent samples. I want to know, does the data suggest that the person on a normal diet exceeds the value of those on a high-fiber diet? So I want to know, is the average normal diet higher than the average high-fiber diet? So again, we're looking at mu1 minus mu2 is equal to 0 versus mu1 minus mu2 is greater than 0, where the sub 1 would indicate a normal diet and sub 2 would indicate a high fiber diet. Unlike the paired case, I now have to figure out an average and a standard deviation for each sample. So I've done the calculations here to show that the average for the normal diet is 27.7. The standard deviation for the normal diet is 5.44. For the high fiber diet, the average is 18.61, and the standard deviation is 5.55. So I'm going to plug into my test statistic now, x1 bar minus x2 bar over the square root of s1 squared over n1 plus s2 squared over n2. So I take all of these values and I plug them into the test statistic, giving me a value of 2.976. Now, how do I come up with the degrees of freedom here? Well, with Welch's, since I have two independent samples, I look at the size of each sample and the number of degrees of freedom that each one of those would give me, and I take the smaller of those two. The first sample has 6 observations in it, leading to 5 degrees of freedom. The second sample has 7 observations in it, leading to 6 degrees of freedom. So 5 would be the smaller of the two. So I'm going to use 5 degrees of freedom. And I was at the 5% level. So I'll go to my t-table. I'll go to the 5 row. And the 0.05 column, because this was a one-sided test. And I see a value of 2.015. Because my test statistic is greater than 2.015, we know we would reject the null hypothesis and conclude that the normal diet has a higher half-life than the high fiber diet. In StatCrunch, we would go to stat, t-stats, to sample with data. So we'll go to stat, t-stats, to sample with data. And I'm going to pick sample 1 to be the normal diet, sample 2 to be the high fiber diet, which I have as in variable 1 and variable 2 columns. Uncheck the pool variances box because we're using Welch's, we're not pooling variances together. I want that mu1 is greater than mu2, and I will hit compute. And notice it gives me my test statistic and a p-value. It tells me the p-value is 0.0065. Let's see if we could come up with that as a range from our t-table. Notice that in the t-table, I would go to the 0.05 row, or the 5 row for 5 degrees of freedom. I would try to find 2.597, and we would end up with a p-value between 0.01 and 0.025. Here it gave me a p-value of 0.0065, which is outside of that range. Why would that happen? Well, remember that when we're doing this test statistic, there is an expression for the degrees of freedom that relates to both sample sizes. It's more convenient to us, and it's a good approximation for us to use the smaller of the 2 degrees of freedom. So our p-value range will probably be higher than the actual p-value, but it's still a good estimate for us. 0.0065 was close to 0.01. Again, notice our test statistic is going to be slightly off of what we calculated because we did do some rounding up here. So let's see if we can do another couple of examples with this. And we're going to do an example where I just give you some information. And do it from some summary stats. Okay, so let me pull up my screen here. And let's say let's suppose that we had mu sub d, we had the null hypothesis that mu sub d was equal to 0 versus the alternative that mu sub d is not equal to 0. And I tell you that d bar is equal to 3.1 and that S sub d is equal to 4.7 and that N is equal to 16. So let's look at then our t statistic. So I'm going to do another paired example. So I know that since this is paired, I'm looking at t as d bar over S sub d over the square root of n, which is 3.1 over 4.7 over the square root of 16, which gives me a t value (2.638). And let's say that alpha is at the 0.02 level. Okay. Well, what am I going to look up? What's my critical value? Well, first of all, note that I have n is 16, so that implies 15 degrees of freedom. Because this is a two-sided test, I will use alpha over 2 as 0.01. I know I'm going to look up then in the 0.01 column of the 15 row to come up with my critical value. So I'm going to go to my t table. I'm going to go to the 15 row. I'm going to go to the 0.01 column, and I see 2.602. Because t is bigger than that, I will reject the null hypothesis. Right? My t-value that I've calculated is bigger than the critical value, which means I've gone further out than I was allowed. So therefore, I will reject the null hypothesis and conclude that these are not equal to each other. How would I calculate the p-value? Well, if I go back to my t-table, I'll look for 2.638. I notice that that is on the 15 row. Between the 0.01 and 0.005 column. So I know that one side has a value, so one side has a value between 0.005 is less than p is less than 0.01. So in order to get both sides, I have to make sure I multiply that by 2, which gives me 0.01 is less than p is less than 0.02. So my overall p-value is less than 0.02, or somewhere between 0.01 and 0.02. I could also do this in StatCrunch. If I go to StatCrunch, I click on Stat, T-Stats, Paired, or actually I want to do one sample with summary, because I've already calculated, I haven't given you any information that you could calculate the difference. I've just given you what the difference is. So I know the average difference was 3.1. I know the sample standard deviation was 4.7. The sample size was 16. And I wanted equal 0 versus not equal 0, and I will compute. And I will see that test statistic of 2.638. I'll also see a p-value of 0.0186, which is between our 0.01 and 0.02 that we calculated. What if I give you an example now where I have, suppose they are independent samples, and I have that mu1, or excuse me, so I have the null hypothesis that mu1 equals mu2 versus the alternative that mu1 is less than mu2. And I tell you that the sample 1 average is 42.3, and the sample 2 average is 46.9, and that S1 is, let's do 8.2, and S2 is 7.3, and that N1 is equal to 24, and N2 is equal to 22. And let's calculate our test statistic then. So this is going to use the Welch's T. T is going to equal x1 bar minus x2 bar over the square root of S1 squared over N1 plus S2 squared over N2, which in this case is going to be 42.3 minus 46.9 over the square root of 8.2 squared over 24 plus 7.3 squared over 22. And if we punch that in on our calculator, take a second here. We get minus 2.01. Let's see, how many degrees of freedom would we have? We would have N1 was 24, leading to 23 degrees of freedom. N2 was 22, leading to 21 degrees of freedom. We take the smaller of those two, which gives me 21 degrees of freedom. And let's say we were looking at the alpha equals 0.025 level. Since this is a one-sided test, I'm going to look up 0.025 column and 21 degrees of freedom, my t-table. So I'll go down to 21. So this is 21 row, and I'll look in the 0.025 column, which I see is 2.08. Now again, since I'm going out to the left, minus 2.01 is not less than minus 2.08. So we fail to reject the null. This says we should walk out 2.08 steps to the left before we would think there was a problem. We've calculated that we've only gone out 2.01 steps to the left, therefore we fail to reject. Again, a way that we can do this in StatCrunch is to go to Stat, T-Stats, ToSample with data. Stat, T-Stats, ToSample with summary. There we go. My first sample mean was 42.3. My standard deviation was 8.2. And N was 24. I had a sample mean of 46.9 for the second one. I had a standard deviation of 7.3 and a sample size of 22. We're not going to pool the variances. We were looking at less than, and we hit compute. And notice that gives me a minus 2.01. The p-value is 0.0252, which is a little more than 0.025. So technically we would reject the null, or we would fail to reject, because this is higher than the threshold of 0.025 that we set. Note that if we would have set a 5% level of significance to begin with, we would have rejected the null hypothesis. Well, hopefully these examples will help you go through the calculations and get through your homework. Again, don't be afraid to use StatCrunch to help you with some calculations. On the exam, I will expect you to be able to calculate the test statistic from the test statistic formula. I will expect you to be able to look some things up in the t-table and make a conclusion based off of that and find a p-value. So with that, this ends the example portion of Lesson 8.